Just wanted to recap a bit about logarithmic scales. The main activity you did on this term is still on Desmos, and I'll make sure there's a link to that in Show My Homework. But we're going to look at something a bit different today about how you can use something called semi-log paper with logarithmic scales. But first off, let's just recap what they are. So on here, we've got an example of bacterial cell growth, which is exponential. And you can see from the table that with every step, it's doubling as it's going down. Now, the graph shows that exponential curve that we're used to for an exponential increase. And that's really useful in lots of ways to have a graph like this. But there is a bit of a problem. If we look at the values here for 160 and at 0, from the graph, they pretty much look like they're just the same amount. But if we look from our table, at 0, it's just one cell. At 160, it's 256 cells. So that's actually a really big increase, but we can't tell that because of the nature of this linear scale, because of how big these values here get towards the end of the graph. Now, even more extreme, if we start it with 2,000 cells, again, it's doubling every time as we go down. Again, we can't really see a difference between 0 and 160. But looking at the values here this time, say 2,000 cells at 0 minutes, at 160, it's over 500,000. So a massive difference. Actually, it's the same increase we had in the last one, but the numbers here show it's a bit more extreme. 500,000 difference, and we can't tell that from the graphs. And that's why we need to use logarithmic scales. So here we've got the graph that we've seen already, and this one shows exactly the same information, but it's using a logarithmic scale. So going up the y-axis, we can see we're multiplying by 10 here, multiplying by 10 here. Every time we're multiplying by 10, it's logarithmic. And an exponential curve on a logarithmic scale will always give us a straight line like we can see going on through here. Now, this has a few different benefits. First one is we can really read different values off. So we were looking at 0 and 160 before. So 160 is going to be this dot here. Now, when we read the values off these now, so we can see 0 is at 1 here. We can see 160 is about here. We can see there is a significant difference between these two. But we must be careful when we're reading off the log scales. The example I've got down the bottom here is for 100 minutes. So on the table here, 100 minutes was 32 cells. On here at 100 minutes, it's here. If we follow across, that's halfway between 10 and 100. Now, we would think that halfway between 10 and 100, that's going to be a difference of 90, that's going to be like 55 or something around that. But we can see from the table it's not, it's going to be 32. So the activity you did before was looking at how to read logarithmic scales like this. So looking here, focusing on the difference between 1 and 10, and we're going 10 squares up, it'd be times 10 again. The next big marking on the scale would be 100, then 1,000, and so on. We break it down into powers. Now, we're starting with 1 is 10 to the power of 0. Remember, anything to the power of 0 is 1. We're going up to 10, which is just 10 to the power of 1. So the 10 divisions as we go up through, each time we're going up 0.1 of a power. Now, if we were to use a calculator to work out what these values actually are, we'd get these. Now, we can see they're not evenly spread. And if we take off some of the values and put them on here, for example, we can see the value here was around 2, so we've put 2 in here. The value here was pretty much 4, and here was almost 8. So what we've done on the scale we've got on this side is we've used these actual values down here, not 10 to the power of something, the actual values, to try and make a bit more sense of our scale. And we can see there's much bigger gaps between 1 and 2 than there are, say, between 4 and 5. And as we go up, the gaps get smaller and smaller each time. The task you did before, you just had that blank logarithmic scale, and maybe you had to read off something, say here, and work out what that was. And the way you learned to do that was say, well, that's about 7/10 up between 10 to the power of 0 and 10 to the power of 1. So that must be about 10 to the power of 0.7, and you'd calculate that, and you'd get an answer something like 5. So it's a useful skill, you need to know it. But sometimes graphs are put on something called semi-log paper, which looks like this, which is much easier to read off. If we had a value here that we need to read off at the same place, well, we can just see it's 5. We don't have to worry about the powers like we were looking at before. Now, if it's not clear at this point, don't worry. What we're going on to do is to look at some examples, and I really think after just a couple of examples, this will make a lot more sense. So we've got a graph here on our semi-log paper. We can see going up the y-axis is logarithmic. So 0.1 here, timesing it by 10, timesing it by 10, timesing it by 10. So that's a logarithmic scale. Going across the x-axis, we can just see it's going up by 5 each time. So we've got a linear scale there. And this is what semi-log graph paper is. One of the axes is logarithmic, the other one is linear. You can also get log graph paper when you need to use a logarithmic scale on both axes, but that's beyond what we need to do. So let's look at some questions to make a bit more sense of this. What's the value of y when x is 15? So reading 15 off the x-axis, nice and straightforward. We follow the line up to the graph, and we're going to read it off from the axes here. Now, sometimes with semi-log paper, it has the odd number or two like these to help you make sense of the scale, but not always. It's a useful hint though, if we count up, so that's 2, so that must be 3, that's 4, that's 5. So when x is 15, y is equal to 5. Next one. Value of y when x is 25. So here's x is 25. We follow up to the line, and then we follow across here. Now that was 0.2 we were shown, so 0.3, 0.4, 0.5, 0.6, 0.7. Y is 0.7 when x is 25. Value of y when x is 17.5. Now remember, the x-axis here is linear, so we read it in a normal way. 17.5 is going to be halfway between 15 and 20. Follow it up to the line, and then we follow it across. And we can see from our markings before that y is just equal to 3. Just going to wipe those markings off so we've got a bit more clarity for the next steps. Clearly I need a bit more practice with this tablet pen, but I'm getting there. Okay, that'll do. So, what's the value of x when y is 0.7? So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and I've just realized that's a rubbish question because that's exactly what we did up here. Okay, but we would find out where 0.7 is, we'd follow the line across, and we'd follow it down, so that would give us x equals 25. Hopefully I've done a better job with this next example. What's the value of x when y is 50? So we're looking here between 10 and 100. So 20, 30, 40. This one is 50. We follow it across the line. Now, Doesn't sit nicely on a vertical line, but that's no problem. We can follow it down carefully as we can. It'll be much easier on exam paper when you've got a ruler you can actually use on a printed sheet. And then we'll have to estimate here about where that is on the scale. So it's a bit over halfway. So I'm going to put down there that we've got x is equal to 3. In a moment, pause the video and have a quick try on these. But first, I want to point out a mistake that you sometimes see with log scales. So here we've got 10 to the power of 1, so 10. 10 to the power of 2, 100, and 10 to the power of 3, 1,000. So we can see as we're going up by a multiple of 10 each time, but not from here. If we do 0 times 10, we don't get 10, we get nothing. So this is a mistake on the scale here. It should be 1 at the base here. So with that in mind, pause the video and have a try with these. So check out the answers to these. It would have been tricky for you doing it just on the screen and judging it, and I'm finding it hard enough just with a drawing tablet here. It would be a lot easier with an exam paper with a ruler. But you should have something round about the answers that I've got there. There's one more set of practice questions. So pause the video, have a go at these, and then come back for the answers. So hopefully your answers look something like the ones I've popped in here. And hopefully not too seasick from the kind of wobbly lines I'm drawing there. Semi-log graph paper does make reading logarithmic scales much easier than without, which we've practiced before. Just a couple of bits to pick up on the side here. Now, when x is equal to 4, so I've put here that y is equal to 63. Now you can hopefully see from the scale here, it looks like it's pretty much halfway between 60 and 70. Remember, halfway between two numbers on a logarithmic scale doesn't mean they're normal arithmetic mean. Okay, so 65 would have been okay here, but halfway between two numbers, halfway between 60 and 70 is nearer 63 on this. Like halfway between 600 and 700 on a log scale would be about 630. And last comment to make is just on the last one here, when y is equal to 2. So we've got that in here. We've read it off the scale. Now, to me, it kind of looks about a quarter of the way across, but I didn't put 1.25. Just because going to 2 decimal places on this seemed a bit ridiculous when it was just a bit of a rough estimate. So 1.2 or 1.3 would have been fine. But all of these answers, there is margin for error on here. So hopefully this makes a bit more sense. Now have a go on the semi-log graph paper question in your revision packs. I think it's maybe about the 3rd question in there. And please let me know if it still doesn't make sense, if you'd like more help with that. Good luck.